Yeah,
Hello.
very good evening to all of you.
Good evening,
Welcome to
ma'am.
Good
the
evening, ma'am.
yeah, welcome to the session. For the coming 5 days, we'll be discussing about solar system and the planets. Hope everybody is ready, right? You already know a lot of information about solar system, right? Like the origin of the solar system, what is solar system composed of, for example, what are the different components of solar system, like the sun, the planets, its moons, dwarf planets, comets, asteroids, planetesimals, right? A lot of things you already know about solar system. We will in this sessions study deeply about the solar system, how it originated, and the condition now, about each of the planet, about sun and its different layers, its process, etc. So today we'll be considering sun, and of course the whole solar system and outlook. We will have a check on it, and then we will have a look at the sun. Yes, and the coming days will be dealing with planets and other smaller objects like moons, asteroids, and comets. Yes, let me share the screen. Yes. So, as a beginning, we'll have a look at the origin and early development of solar system. We know that, why we study a lot about solar system, because it's like studying about ourselves, right? We are living on Earth, which is a planet revolving around the sun. So the the term solar system include everything and anything which is near to the sun, right?
Yes,
So
ma'am.
sun is said to be, yeah, the center of mass of the universe. I mean, the solar system, where every planets revolve around it. But and you know that as senior student, I am sure that you know that it's not like the planets and everything is revolving around the sun, but there is a common center of mass, and all the planets are revolving around that particular center of mass. Even the sun is revolving around it, but just because the center of mass is inside the sun, because the sun is very massive. Talk about the mass of the sun. Can anyone tell me how massive is sun? Approximately how massive is sun? Any idea?
Excuse me, ma'am.
Yes.
Ma'am, I think around 3,000 Earths can fit around the sun.
3,000 earth. Okay.
No, ma'am. It is actually 1.2 billion Earths.
1.2 billion. Oh,
Not
it's
billion,
actually,
but not billion, not billion. 1.2
It's a million.
billion
anyway.
MI.
Yeah, we'll study about that in the coming slides. Actually, sun is 2 into 10 raised to 30 kilograms massive. That is 1 followed by 30 zeros. That massive is sun. Almost 99.85% of the mass of the whole solar system is within the sun. Yes, let's see. So, how such a system is formed? Where do you think the sun is formed? Of course, like any stars in the universe, sun is formed within a nebula. Nebula, you may have heard the term, right? Nebula means a cloud of gases. Mostly hydrogen and helium will be in the nebula. And inside, maybe you have heard about crab nebula, horsehead nebula, such beautiful pictures of and beautiful shapes, which was taken by Hubble Space Telescope. You may have, yeah. And Eagle Nebula, and number of nebulas are there. Nebula means a clump of, like a group, like I mean a cloud of gases, which is seen in the interstellar space. So inside this gaseous clouds, what will happen? Of course, the gases, it can't stay still, right? It will move around. As it move around, it'll collide with the other gaseous particles, molecules. As it is colliding, it'll stick together, And just like the condensation theory that we study in the classes, it's when it stick together, it becomes a clump. So these smaller clumps are produced within the nebula. These clumps move each other and they stick together, and it will become a bigger ball-like structure, a bigger clump. As it is, grow in size, its gravitational force become immense. So what will happen then? More the clump will become more and more massive and larger. But one thing is there, as the mass is increasing, of course, gravitational force within the clump will increase, right? Then what will happen? Due to the gravitational force, this ball begins to shrink. As it is shrinking, inside in the core of the clump, it will become hotter. As the gravitational force or mass increases, it will attract more and more gaseous particles, more and more gaseous clumps. And what will happen then? Yeah, it begins to shrink, and inside temperature begins to, it'll become hotter. Yeah, increase. It will become hotter and hotter. And once it reaches, if it reaches really massive, and if it reaches some 10 raised to 9 Kelvin, then a special process, a unique process happens inside that particular stuff. What is it called? Anybody?
Nuclear fusion.
Very good. That's called a nuclear fusion. So once there is nuclear fusion, what will happen? Towards the center, there is gravitational force. And due to the nuclear fusion inside, there is radiation force which is acting outwards. Because, the photons created during hydrogen-hydrogen fusion, it is coming out of the system, right? So the radiation force will be towards outside. When this gravitational force and radiational force, the inward gravitational force and outward radiational force, when they balances, we call it a star actually. Okay, that's how a star is formed. And this is not just a story of a particular star, but yeah, almost all of the stars are formed like this. Excuse for the sun. Sun is also formed like this. Once it was a protostar and became a main sequence star once it attained the particular balance. And due to many other processes that we will discuss in the coming slides, there, around the sun, there were planetesimals, there were smaller particles again, and they clumped together, and the planets were formed, and other solar system objects were formed, and all these system, what we call solar system, it itself is moving around, moving inside the about our galaxy, right? And we are one of the arms of galaxies, and we are actually revolving the center of the galaxy. So our solar system, part of Milky Way, consists of 8 planets actually. Yeah, 64 known moons, many asteroids, millions of comets and meteoroids, as well as interplanetary dust and gases.
Excuse me, ma'am.
Yes.
What is the barrier between the end of the solar system? What counts as the end of the solar system?
Sorry? Or edge of the no, okay, I understood. See, edge of the solar system means there is no clear-cut edge for solar system. We call it, after the Oort cloud, say some 2 light years from the center of the sun. If you call that way, it's like it's called the heliosphere, which means the effect of sun. I mean the gravitational effect of sun to how much distance or how much extent it reaches, we call it a heliosphere. But there is no any a particular edge. For example, take a bar magnet. Can you tell me where the magnetic field of the bar magnet edges or just finishes off?
It actually extends till where the magnetic field ends. Like
Yeah,
the strength of the magnet, it depends on the strength.
I mean, yeah, but so theoretically, it is like it's infinity, right? But in the case of the solar system, it is more of like the heliosphere itself. You can say after the Oort cloud.
Okay, ma'am. Thank you.
No problem. Yes.
Excuse me, ma'am.
Yes.
Yeah, ma'am, could you elaborate a little bit on heliosphere because I really want to write about that.
Ah.
I'd
Okay.
like to know about that.
Okay. So heliosphere. Helio means something related to sun. Okay. So
Excuse me,
yes, please.
Miss, you were talking about the outward radiational force. So
Yes.
by that, do you mean the sun rays?
Not exactly the sun rays. Sun rays are outside, right? Outside the
Yeah.
sun. I'm talking about the forces inside the sun. I mean, in the core, when fusion happens, fusion happens, then photons are generated, right? Photons are
Yeah.
actually packets of energy. When they are moving out, it is like a ray, a wave of energy which is coming out of the core towards the surface, right?
Okay.
That's what.
Understood.
Yeah. Yes.
So correct
And
me if I'm wrong. So you said that inward gravitational force and outward radiational force is equal. That is when the sun is formed. Is this correct?
yes, yes, not just the sun, but the star is formed.
Okay. Thank you.
Yeah, no problem. Yeah, you talked about heliosphere. So, the sun sends out constant flow of charged particles. You know about that, right? Like along with the ray, a lot of charged particles are being, um, you know, thrown out of the sun. Like it's being radiated
Ma'am.
out of the sun. So, can I complete this, please? So
Yes, ma'am.
it's called the solar wind, and it ultimately travels past all the planets. Okay, I mean, say from Sun to Neptune, and you consider that distance and 3 times that distance. You just consider that in the interstellar medium. Then you will get a bubble of solar particles, right? In every direction, the sun is sending radiations, right? So say
Right.
from yeah, so that whole bubble is called heliosphere.
Right. Ma'am, just a follow-up question for this. So,
Yeah.
like our Earth, okay, it has a magnetosphere. So, is it something like that or it's something totally different?
I didn't get that. Fuel you asked about.
No, our planet Earth has magnetosphere, right?
Magnetic field, yeah.
Yeah.
Magnetosphere, yes.
So, is the heliosphere something similar to that or is it totally
No,
different?
even sun has its own magnetic field. It's not just the magnetic effect, but solar wind means particles. Charged
Cosmic
particles are
rays. Cosmic rays.
cosmic rays are coming from outside the solar system, maybe like cosmic rays are coming from different parts of the universe. It's not just the cosmic rays, but cosmic rays also contains charged particles, that's right. But such charged particles, when it is provided from the sun, we call it solar winds, right?
Solar winds, all right.
Yeah. So the extent of solar wind, say, consider just the distance from sun to Pluto, 3 times that distance. That up to that much level, you can get the solar effect. I mean, the wind, the particles provided from the sun. So that much distance, if you just imagine a bubble around all that, we can just call it. There is no clear extension like, okay, from this distance to this distance is a heliosphere. Nothing like that. This is an approximate distance. And there is no actual bubble there. It's just like we imagine so.
I put that in perspective.
Ma'am, what
Yeah.
is angular momentum?
Oh, yeah, angular momentum. See, linear momentum, right? P is equal to mv, you have studied about it, right?
Yes, ma'am.
Yeah, just like that. Angular momentum means, it is the rotational analog of linear momentum.
Okay, ma'am.
Yeah.
Ma'am,
Yes.
you said that a nebula is gas, so technically, how does a surface form for any star when it's made out of gas?
Actually, there is no solid surface for any star, right? It's the gaseous sphere, right?
Okay.
Yeah. There is no, so we cannot stand anywhere like there is no solid platform. It's just gaseous, like very hot gas in the form of plasma. So I
Wait,
think, yeah, yes.
yeah, sorry to interrupt again, but I just had one more question regarding the sun.
Mhm.
The question is, why is this sun's corona more hotter than the surface?
Yeah, actually, we are coming to that. It's in the slides, in the coming slides. Okay, as we go through the slides, you'll understand that. Okay, I mean, you won't understand that. I don't have answer for why corona is hotter than that of the photosphere, because that is actually a question that is being unanswered for a long time.
Ma'am,
There are many theories like hypotheses regarding that, but it's not finalized yet.
Ma'am,
Yeah.
on the last point that you mentioned for nebula contraction, is it due to like the collisions canceling out all the motion in different directions and just leaving the rotation in the specific plane as shown in the bottom?
Yeah, something like that. Let's have a look at the figure or slide. Yes. So the cloud of interstellar dust and gases, and that's what we call it nebula, when it begins to contract, it becomes denser and hotter, and eventually forming a star at the center. So, see, inside the star, it is completely a mess. A lot of activities are going on there. When it is contracting, like the pressure is increasing, the heat, the temperature is increasing, etc. So as it contracts, the cloud spins faster and faster. Okay, and it forms a flattened pancake-like shaped disk. It is due to the angular moment, and then such a disk is formed. For example, um, you may have studied that in the classes, maybe like when a person is revolving. If you're rotating yourself, then which is better? Like if you are just holding your hands close to you, then speed increases, right? Or have you seen how pottery is made? Huh? When it is
Yes, ma'am.
revolved, then it will become flat, right? Hmm? Got it? Understood?
Yes, ma'am.
And that's how this flattened shape is formed. Yes. So there is this theory called nebular contraction, by which solar nebula, which is a nebula in a sun created from, this flattened pancake is usually referred to as solar nebula, since it will form our solar system. The idea that planets form from such disk is called the nebular theory, and it's not like we are just hypothesizing that, but we have seen such systems in universe, in other planets, like in other systems we have seen such systems. So old nebular theory, the old one, which is wrong, as we know now, clumps of matter would not form from the gas, as they would have dispersed and not formed planets. So when the stars are formed, yes, of course nebular theory is okay, but when the how the planets are formed, that is not discussed in the nebular theory. But there is another theory called condensation theory, which is a part of nebular theory, in the way like the sun is formed from the nebula, but it's not the same process by which planets are formed. So What is the key ingredient of planets? Raw material for the planet formation. It is the interstellar dust in the solar nebula. So this dust, it acts as condensation nuclei, or you say microscopic platforms to which other atoms can attach. That's called condensation nuclei. Just like the way how clouds are formed, there will be a small cloud particle. It's called the condensation nuclei, to which all these others will come and attach. And that's how this so the dust acts as a condensation nuclei and helps the cloud cool enough for condensation to occur in the first place.
Excuse me, ma'am.
Yes.
Can you explain nebula contraction again? I couldn't understand it.
Nebula.
Contraction.
Oh, in nebula contraction means, inside the nebula, see, just like you see, when the particles, the molecules within the nebula will be moving together, and it will form a clump like this. This is the nebula contraction, because the cloud nebula is getting contracted here, right? It is shrinking. As it is shrinking, what will happen? The temperature and pressure inside will increase. And as it is shrinking, it revolves, it rotates faster. And when it is rotating faster, it will form this kind of a shape, a flattened disc shape. Okay.
Okay, ma'am.
Yes.
And why does it form a flattened disc shape?
Just like in the pottery, when the angular momentum is increased, the height of the system is decreased while the width is increased. That is a like, yeah. When just like when something is revolve faster, then it will become flatter. Okay. Yeah.
I
Yes.
suppose a large number of these planetary bodies are formed during the initial stages of star formation.
Sorry, once again, can you please ask?
Ma'am, a large number of these planetary bodies are formed during the initial stages of star formation.
Yeah,
But
initial stage of star formation, a lot of such planetesimals were there.
but only few are perfectly placed such that they are, begin to orbit the star. The rest are either
No,
in
it's not like they begin to orbit the star, but the whole it was already revolving the star. Okay, so on the go, they hit together. But in different speeds, they were revolving around. But on the go, they hit together, and sometimes they clump together. That's how, when a critical mass is achieved, then gravitational force become high. When gravitational force become high, it will attract more and more planetesimals, more and more rocks, and it become bigger ones.
So my point is that a planet is formed when many particles of this, collide together. So in case of uh, if during the collision it flies towards the star or gets displaced, it has a high probability of not orbiting the star.
Not orbiting the star. It is actually, unless it is hit very hard so that it will attain the escape velocity of solar system, it can't just go away like that. If you throw a stone, it will come back to earth, right? Just like that, even solar system its own has a high escape velocity. So if the speed is more than that, of course it can escape the system. But most of the objects, the speed is less than that of the escape velocity.
They can not
Okay.
only escape, they can fall into the sun's surface also.
Yeah, that is possible actually. For example, consider Mercury. When we study the Mercury slide, you'll see that Mercury even doesn't have a crust because that was accreted by the sun. That is possible. But
Sure,
once
ma'am.
it achieved a particular orbit, then it is the chance of getting into the sun is less.
Yes, ma'am.
Yes. So according to the condensation theory, the planets formed in three distinct stages. The first two apply to all the planets, and the third applies only to the Jovian balls. The first stage is, there are three stages. That there are different types of planets, right? For example, the first four planets, Mercury, Venus, Earth, and Mars. It's called the terrestrial planets or inner planets, etc. And then after Mars, we do have an asteroid belt, and then there is Jupiter and Saturn. We call it Jovian or gaseous planet, and Jovian means Jupiter-like planets. And then there is icy planets, that is Saturn and Neptune. Uranus and Neptune. So for the first four planets, so it goes by dust grains in the solar nebula formed the condensation nuclei, and these clumps then stick to other clumps, causing the clumps to grow in size rapidly. Then there is a process of accretion. So such accretion disks were formed. Accretion means gradual growth of objects by collision and sticking. So these the pro due used during the process of accretion, um, it creates objects of few hundred kilometer across. So the size of the object will become, becoming larger and larger. So at the end of the first stage, which is this accretion stage, solar system consisted of hydrogen and helium gas and millions of planetesimals. Object size of small moons having gravitational fields just strong enough to affect their neighbors. Then there is stage two, which is the gravitational force between the planetesimal caused them to collide and merge. Okay, so in first stage, due to accretion process, planetesimals were made, and the second process, this planetesimals had gravitational force that could, that could attract the neighbors. It can't go far beyond, but the neighbors, so they stick together and became larger objects. And because larger objects have stronger gravitational pulls, eventually almost all of this planetesimals material was swept into a few large protoplanets. And the asteroids and comets originated as collisions between the planetesimals and protoplanets, send out small chunks of materials that escape capture. So after 100 million years, we have 8 protoplanets, then dozens of proto-moons, glowing protosun at the center. So roughly a billion years were required to sweep the solar system clear of interplanetary trash. This is a period of intense meteoritic bombardment whose effects on the moon and elsewhere are still evident today. So the third one is the making of Jovian planets. So there are two conflicting views on how the Jovian planets are moved. So the first one is four largest protoplanets became massive enough to enter a third stage of evolution. That is sweeping up large amount of gas directly from the solar nebula. So these four became larger. And the second view is giant planets formed through the instabilities in the cool outer regions of the solar nebula, mimicking on small scales of the collapse of the initial interstellar cloud. So these are the two views. Anyway, you can understand that when the sun was formed, it was highly active. The young star was very active. It was emitting a lot of energy. And the solar storms actually wiped out the lighter elements from its nearby. Nearby the sun, there are less lighter elements, and it was moved, away to the outskirts of the system that at that point of time. And that's why you can see the inner planets are having heavier elements in it, while the outer planets, they have a lighter particles in it, right? The hydrogen and helium mostly. In the inside we have silicon, iron like elements. Okay, so many of the Jovian moons probably also formed by accretion by these bigger planetesimals. Eventually, the sun blew away any remaining gas between the planets, which is why we don't see it today. The outer planets must have been formed before the nebular gas dispersed. I mean, even that's why in the outside, these from Jupiter onwards, there are many satellites, right? More than 50 satellites. So how satellites in the sense moons for Jupiter and Saturn. How is that possible? This is a reason why. And we see almost neat a solar system now, which is deprived of the dust particles between the planets, right? And it is because of this long process.
Excuse me,
So, yes, please.
ma'am, I couldn't understand making the Jovian planet.
Okay. Making the Jovian planets means these many of these moons, Jovian moons, it is actually in the previous slides we were talking about the planet formation, right? And in this slide we talked about two views of making the Jovian planets. This is the extension of the slide. Oh, sorry, this slide talking about the Jovian satellites. I mean Jovian moons.
Ma'am, I still didn't understand the second view of how Jovian planets were
Okay.
made.
So you understand the first view, right? Where the four largest protoplanets, these four largest, talking from Jupiter to Neptune, they became large enough, so they directly swept a large amount of gas from the solar nebula. So that is the first view. The second view is these giant planets formed through instabilities in the cool outer regions, because in those areas the gravitational field produced by the sun is less than that of the inner planets, right?
Yeah.
So just they mimic, actually it is like if sun was not there, Jupiter could have been a star. So they mimic the process of solar nebular contraction. That's why they actually accreted all these planetesimals nearby towards them. That's why
Okay.
a lot of moons. Yeah, that's the second view.
All right.
Okay. So the differentiation of the solar system. I mean, um, just talk about the initial stages of the solar system now. The closer to protosun, the hotter the temperature. I mean, when we are going near to the sun, the temperature is of course increasing, right? So the temperature determines what could form where and when. Because the sun, the mass of the sun, the position and mass of the sun can determine the position of the planets formed. It's not like, for example, you may have heard that many of the planets like Neptune and Uranus, etc., they were not found by just looking through the telescope. Mathematically, considering the mass of the sun and the orbit of other planets, we can determine in which region there is a probability of finding another planet. Okay, it's all mathematics. So sun can determine the position of the planets, and then the innermost regions, for example, Mercury, only metallic grains could form due to this high temperature. If just think about if the temperature is rise, of course the gases get more energy, right? When it get more energy, of course, it will fly off because it will escape the planetary systems. So that's why in the inner planets, heavier elements are there. At 1 AU means astronomical unit, which is the average distance between the sun and Earth. So here there is formation of silicates. Only at that time, age of the protosun, when the sun was forming, beyond 3 or 4 astronomical unit, water ice could exist. Water was not about existing in the inner planets.
Ma'am,
Yes.
if only after 3 or 4 astronomical units water could condense, then how come water can condense on Earth?
I mean, at that time there was no water on Earth. Water on Earth supposed to be, in the beginning, it's not made from Earth. The water from Earth is said to be from asteroids, carbonaceous asteroids, which came from the outer layers, outer solar system. Okay, I am talking about not the present sun situation, but when the sun was a proto-sun. That time, like I told you, the energy is very, there is huge energy for it. When somebody is young, like you people, you have a lot of energy, right? But when it ages, of course, when he or she reaches her 20s or 30s, stability will be there. The thing will attain the stability, right? Just like now, the sun is not a proto-sun now. Sun is a main sequence star now. Understood?
So, ma'am, the Earth is still 1 AU away from the sun.
Yes.
And because the water came on Earth before the sun was at its full power, that's why water exists on Earth.
No, no. Water came on Earth after the actually sun became, I mean, relatively stable.
So that is why it condensed.
Yeah, of course, yes. And at that time, Earth was not in a condition, a cooler condition. It was actually volcanoes everywhere at that period. And it was not condensed but was in a gaseous forms in the atmosphere. And when Earth attained some stability, it rained. When it condensed, it rained for hundreds of years. That's how the oceans and the water bodies were formed.
Okay,
Yeah.
all right.
Okay.
And can you tell about proto-sun again?
Proto-sun means it is in the early stage of sun. That's all. When the sun is about not the sun that we see now, it was about to be a star, but not a star. That stage, early stage of sun.
Okay.
Yes. Now let's have a look at the general characteristics of solar system, the planetary orbits and rotation. So the planet and satellite orbits are in common plane. That is for sure, right? Because it was formed out of this accretion disk. So most of these were formed in a same plane. I mean, consider all these planets. They are in the same plane, and then nearly all planet and satellite orbiter and spin motions are in the same direction. There is one exception for this. Can you please name it? Name the planet.
Uranus.
No.
Uranus.
Uranus actually revolving direction is same. Only the axis tilt is there. Axis tilt is almost 90 degrees.
Venus. Mercury.
Yes. No, it's Venus. Yes, it is Venus. And then the rotation axis of nearly all planets and satellites are roughly perpendicular to the plane of the ecliptic. Now, I'll tell you some more characteristics like physical and chemical properties of planets. The terrestrial planets, they are small. Terrestrial planets means planets which looks like, I mean, more like Earth. For example, this Mercury, Venus, and Mars. Terrestrial planets are small, but they're heavier. I mean, they're denser, right? And are composed of rock and metallic elements. Which planet has the most density in solar system?
Earth.
Yes, that is right. Then the Jovian planets, they have larger, low density, and are composed of gases and frozen compounds.
Ma'am, does
Yeah.
Saturn have the lowest density?
Saturn has the, yes, it is. You may
Yes.
have heard the joke, right? If you can take Saturn and put it in on ocean, it will just float.
Yes, ma'am.
Yeah. Now, now the interplanetary material. The rotation of the sun. Do you know how the sun rotates? What is the rotational period of sun?
Ma'am,
Ma'am,
11
25 days.
Yes, that is right. Actually, you just not, it's an average value because have you seen different stripes, different layers around the Jupiter? You can
Yes,
see that they
miss.
are rotating in a different speed, right?
Yes, miss.
Yeah, just like that. Actually, even sun also in the polar region, it rotates faster, and in the equator region, it rotates slower. So on an average, we can just call it some 25 days. The equator days, it is almost 30 days, and in the polar, I think 15 or something. So when you average the whole thing, you'll get some 25 days. That is rotational speed of sun. And then the interplanetary material, yeah. Existence and location of asteroid belt and distribution of interplanetary dust. See, uh, consider if we did not have an asteroid belt, then what will happen? These things will be continuously flying around the solar system and hitting everything, right?
Ma'am,
Yes,
can
That,
you
ma'am.
tell about the rotation of the sun, please? I didn't understand.
see, rotation of the sun means sun is not a, solid body, right? It's a gaseous body. So different portions of the sun, like the equator part of the sun, revolves slower than that of the polar regions.
Okay, okay.
Yeah. So you may have heard about meteorites, right? They are the visitors from outer space. So let me ask you one doubt. You may have heard about different terminologies related to this, like meteoroids, meteors, and meteorites. Can you differentiate between them? Anybody?
Miss, can I say?
Meteors
Yes, you can
burn
say.
out in the outer space, but I think that meteorites come inside the Earth and then strike on the Earth.
That is true.
And
Yes.
meteorites are basically what revolve around them in the asteroid belts.
Yeah, maybe in astronaut belts, maybe not in asteroids, just like asteroids.
Yeah.
Anything
Miss,
which revolves, yeah.
miss, I'm not sure whether I'm correct, but meteorites are when they are in space, then and meteors are when they are like they are in the Earth's atmosphere, and meteors are when they crash on the Earth's surface.
But actually, there is a small error in that. It's okay, I'll correct it. Meteoroids are when they are outside the space. Meteors when they enter the Earth's atmosphere, and meteorite when they are on the surface of the Earth.
Yes, miss, I knew it was something like that. I got mixed up.
It's okay, no problem. Yes, but yeah, So meteors means, whenever these meteoroids, when they enter the Earth's atmosphere due to friction, temperature will rise and they'll burn up. That's how we see shooting stars. Have you seen shooting stars, anybody?
Yes, ma'am.
No,
Yes,
ma'am.
ma'am. No, ma'am. No, ma'am.
Actually, people who are living in village side, they are lucky. They can have a look at the shooting star because there is no light pollution. But the city people, all the time there is a light pollution, right? At night we have
Yes.
street lights, and morning we have sun. But in village, at night, it's if it is completely dark, you can just look at the sky, and after some, like, you can see, I have seen it a number of times. Like sometimes we can see meteor showers, but when I am in the city side, never. Even stars are not visible.
Yes, ma'am.
Yeah, both air pollution and light pollution.
Ma'am, I did not understand one sentence.
Yeah, please.
In the previous slide, it was written that rotation axis of nearly all planets and satellites are nearly perpendicular to the plane of the ecliptic. I did not understand this.
Okay, it means that, see, what is the plane of the eclipse? See, what is the what is ecliptic means, first of all? Any idea, anybody?
No, ma'am.
Oh, okay. I need a picture to show that. See, plane of ecliptic just means that consider an imaginary plane, mm, which uh, in which Earth is revolving around the sun. When Earth is
Okay.
orbiting around the sun, just consider that plane. That is a plane of ecliptic.
Okay.
Where is it? The previous. This is right. And then the rotational axis means uh, rotational axis means the tilt of the planet's rotation.
Okay.
Apart from Uranus, every other planet, it's almost away from the plane of ecliptic, right?
Yeah.
For example, in the case Earth's tilt is 23 degrees, right? Which means 90 minus 23. That is, how much is that? 67 degrees from the ecliptic. Okay. So it's almost perpendicular, right?
Perpendicular is crossing.
90 degree. So closer
Okay.
to perpendicular. That is why it's called almost.
All
Apart
right.
from Uranus, every other planet has a larger angle between the tilt and ecliptic.
What is the angular tilt?
Angular tilt. See, angular tilt means consider in which aspect you are asking?
No, in like you said that it is more near the ecliptic tilt than the angular tilt.
No, not the angular tilt. I mean rotational tilt. Tilt
So
means,
what?
see, tilt is, for example, Earth's tilt is 23, rotational tilt is 23 degree.
Yeah.
Yeah, just like that, that tilt, I mean, that consider a line where, the axis, I mean, that axis, angle between that axis, rotational axis, and the plane of ecliptics, it is more towards 90 degree, more towards perpendicular, right?
Yes.
Yeah, it's a general characteristics. One exception is there, that is Uranus.
Okay. All right.
Yes. Yeah. So we studied, yeah, meteorites are believed to be pieces of materials that originated in the formation of the solar system about some 4.6 billion years ago. And you can see here a crater, right? When these meteors are hit on Earth, craters are formed. On Earth, we cannot see much craters. Why is that? Any guesses?
The tectonic plates.
Tectonic plates. What about the tectonic plates?
Their movement.
Ma'am, effects of
Okay.
the
See, more than that, you can have weathering, atmospheric and wind weathering, rain, water is there. You can just patch up all those craters, right?
Lot of elements to fill up the craters.
Sorry?
There are like lot of elements, water, dirt, everything to fill up the craters.
Yeah, exactly. Yes. So, yeah, that is regarding that slide was about the origin of the universe. I mean, not the universe, the solar system. And in the coming slide, we'll study more about the sun. Okay. Now about the sun, I'll just share the screen. Yeah. So our star or sun. These are the sun's vital statistics. The mass is almost 2 into 10 raised to 30 kilograms. It is 3.3 into 10 raised to 5 mass of Earth. Okay. Then the visual radius is 6.96 into 10 raised to 5 kilometers, which is 109 mass of, radius of Earth, which means if you just in a line, if you just join 109 Earths, say in around 110 round Earths, you will get the size, I mean the diameter of the sun. Okay. Then yeah, the density, it is 1410 kilogram per meter cube. Yeah, and the surface temperature. Surface temperature means temperature at the photosphere is almost 6000 Kelvin. While the central temperature is 15.5 to 10 raised to 6 Kelvin. Yes. So the sun contains more than 99.85% of the total mass of the solar system. And if you put all the planets into the solar system, into the sun, I mean, if you just take all the, including all the planets, all other things, you just filling the sun, it won't be filling up the volume. So 110 Earths or 10 Jupiters fit across the diameter of the sun. Okay. Now, regarding the activities of the sun, it was Galileo who for the first time found that sun is not a permanent body where nothing is happening, but many things are happening in the sun. For example, sun's activity is not a permanent one. It is changing. I mean, there is a cyclic order by which the activities of the within the sun is changing. For example, there is this 13-year cycle for sunspots. At some years, the sunspot number will be very high, and in some years it will be less. It means that there is this periodicity in solar activities. So inside, if you talk about the interior of the sun, it has three layers: the core, radiative zone, and the convective zone. And the energy generated in the core of the sun propagates outwards through these different layers and finally through the atmosphere of the sun. It takes millions of years for this process, right? Because from the surface of the earth surface of the sun to earth, how much time it will take for the rays to come?
8 minutes.
8 minutes.
8 minutes and 20 seconds. But within the sun, from the core to the photosphere, it will take millions of years. due to it's not coming straightly, but having a different, like it's actually dense, and it interacts with everything as it travels from the core to the surface. And now the different suns are, there is the core in the center, there is core in the center, and there is a radiative zone, and there is, you can see here, the convective zone. These are the three zones in the sun: core, radiative zone, and convective zone. And not only that, there is sun's atmosphere, which is photosphere, chromosphere, and corona. Photosphere is the surface of the sun that we see. Okay, their temperature is actually less, almost 5,800 Kelvin. And in the chromosphere, the temperature, it's also called the red layer, which is, when we use a hydrogen filter. Hydrogen filter, you know about that? Like, we cannot look at the sun with naked eye. We need different filters to study the sun. So if you are using a hydrogen filter, then you will see chromosphere. It's a red layer, red colored layer observed when we are using a hydrogen filter, and the temperature, average temperature there is 10,000 Kelvin. Now, corona, which we can
So,
only
ma'am,
see.
the chromosphere is below the photosphere.
Sorry,
The chromosphere is below the photosphere.
chromosphere is below the photosphere. Let me make sure. No, it's after photosphere. It's above the photosphere, right? What determines the rotation, the revolutionary period of Earth? It is the combined activity. It is the things present inside the sun. Maybe the size of the sun, the mass of the sun. There are different intrinsic characteristics for for a particular physical and chemical characteristics for a celestial object, right? That determines the activities. For example, you can see here, this is inside the sun, and here you have troposphere, the surface, and then you have the chromosphere. See this light yellow color. Okay, and this is the corona. Got it?
Yes, ma'am.
Okay. Yeah. Now, now I would like to tell you about the sunspots. See, so these sunspots are actually formed where the magnetic activity in the particular, region on the surface of the sun is very high. Like, it can be many fold higher than that of the adjacent region. So due to this higher activity of magnetic field, what will happen? The temperature at that particular region, it will be less. Okay. So it is seen in dark color. So here, if you take a particular sunspot, you can know there is a penumbra region, which is this shade, not much darker region. And here you can see a darker region. Here temperature is very less compared to here. But in the whole system, temperature is less than that of here. Okay. This is a
Ma'am, why does it
penumbra.
happen that the temperature of the sun increases, the color changes?
And not the color actually. It's the intensity of light emitted from that particular region is less because it is cooler compared to the other region. That's why we see it darker. It's not just a
No,
color.
like when there are very large supergiant stars, they shine a blue color. So why is
Oh,
that
no.
different?
There is, please don't combine those, because that is another thing. That's about the color of the star. Like, blue star indicates a lot of energy is being emitted, and a red star indicates less energy is emitted. Yes, that is true that sun is actually a G2V star, which means it emits, it's a medium star. It's a medium mean sequence star. There are many stars which are bigger than and emitting more energy than that of sun. But this is different from that. This is happening within the. It's like a small spot in the surface of the sun itself.
No, ma'am, but like,
Oh.
why is the light different from those stars? The color of light.
Because it is cooler region here. Due to magnetic activities here, it's not the color. See, color and intensity are different things, right? If something, okay, I will tell you with small example. If consider a light which is shining very bright, okay. If you just
Okay.
paste something like if you just stick some dark, I mean paper into it, such that light is not coming from there, but from the adjacent regions light are coming. You just stick any colored paper, let it be blue, green, yellow, but still if it is opaque, you will see it as dark colored, right?
Yeah.
Yeah, just that is happening here.
Okay.
It is just dark colored. Okay. Yes. So yeah, these are called pores. These in the sense, let me take a point. These, can you see these? These are called pores. This is umbra, this is penumbra, and these are pores. Yes. So yeah, it was Galileo Galilei who for the first time found it. So these sunspots, they are having a 11-year cycle, and during the cycle, the comparing, sometimes it is the number of sunspots are more, and sometimes it is less. Yes. Now, yeah, here there is this examination of sun's surface, and found that, see how this is moving, right? So this movement, using this movement, we can assess that the sun's rotation takes place about 4 weeks. March 9, 10, 11, 12, 13. It just moved from here to here. From March 5 to here, one cycle, March 16, and then April 1 to April 13. It's just moving right like this, right? It's not moving actually, it's the sun rotating actually. Yeah, now I want to talk to you about, yeah, this thing. There are many activities which is happening in the sun. For example, prominences. So prominences are, you can see here, this, this, it looks like some outburst, right? This burst is having anchored. It is having attachment to the sun surface, but it is bursting towards the corona. This kind of an event is called prominence. Okay, what is a prominence? It is,
Ma'am,
yes.
I think it like a solar flares.
There are difference between solar flare, because solar flare is this. There is no attack. It's like, it's just an outburst. But this thing has a I mean structure, right? They are large, bright feature extending outwards the sun's surface. It is closer to solar flare, but solar flares are just like fire. It's just outbursting. But these things, there are two legs which is attached to the sun. Okay. It is anchored to the surface of the sun.
So, ma'am, so it's like it bursts out, but the sun's own gravity brings it back. Something like that.
Exactly. And these are solar flares.
Does the sun's gravity have no effect on them, ma'am?
Sorry?
Does the sun's gravity have no effect on them?
Effect on what?
Solar flares.
Yes, sure. It's not like, see, sun's gravity has effect on everything closer to it. But here, the structure is different. Here you can see there is no, it's irregular in shape. There is no particular structure. It's of course it is attached, but there is no, legs that can be structured here.
Yes, ma'am.
Yes. So,
Ma'am, can you just please go back 2 to 3 slides so I can take a screenshot?
sorry, which one?
The 3 slides before.
This one.
Yeah. No, after this. The 3 slides after this.
This one.
The next one also.
This one.
Yeah, and the next one.
This one.
Thank you.
Yeah.
Yeah.
Yes, and yeah, now the sun also ejects a stream of charged particle into space, and that is what we call the solar wind. Okay. And now there is another thing called coronal mass ejection. That is actually, you can see here the coronal mass ejection. See, it is a bigger phenomenon. In coronal mass ejection, what is happening? They are
The layer of
yes,
corona is being ejected into the space.
exactly. There is expulsion of plasma and magnetic field from the sun's corona. Actually, they can eject billions and tons of coronal material. And yeah, it's like it is these coronal mass ejections are sometimes, can have effects on Earth. It is ejected outwards, not coming back to the sun, but it is ejected outwards. Sometimes our systems can get affected. For example, our communication system or navigation system, it can get affected due to this.
Miss,
Yes.
which of these causes the auroras?
Oh, auroras are caused by solar wind, but when it reaches Earth's magnetic field, it interacts with Earth's magnetic field. In the polar region, the magnetic flux is more. That's why, the solar wind has solar particles in it. When it interacts with our Earth's magnetic field, then auroras are made, formed.
Okay, miss.
Yeah.
Thank you.
Ma'am,
Yes.
ma'am, I wanted to ask that when a solar eclipse happens, we are able to see these coronas.
Yes, yeah, that's right.
So does this have something to do with the CMEs?
No, no. It's not about CMEs. CMEs can eject, but not during, say, it's completely different processes. Sun doesn't know that it's being eclipsed. Okay, it's like we are.
No, ma'am, I'm trying
Yeah.
to ask that do we see the sun's outer layer corona or do we see the ejections?
No,
That's
we
what
see
I'm trying to
outer
ask.
layer corona.
Okay, ma'am.
Excuse me, ma'am.
Yes.
Ma'am, can you tell me again about coronal mass ejection? Ma'am, I couldn't understand.
Coronal mass ejection means ejection of solar particle within the magnetic field towards, outside the sun. The coronal mass ejection means particle, the masses which is in the corona is being ejected outwards. Okay. It can reach, to the maybe Earth or Mars, etc. Yes. Now
Ma'am, in
I
the last
think
slide, there was
yeah.
the term HA in the slide in this one. That above the photosphere, the chromosphere is characterized by the color red from HA emissions.
Which one? This slide?
3 slides before. 3 slides before. So what are HA emissions?
Where is? Oh, yeah. This is actually not in your syllabus. That's why I didn't say that. It means above the photosphere, the chromosphere is characterized by its red color. It's like H alpha in the sense the hydrogen, emission. Alpha particle means 2 protons. I mean, you can say the helium nucleus is an alpha particle.
So an helium particle is an alpha particle.
Yes, nucleus of helium atom is actually alpha particle because it has 2 protons. Right?
Yeah.
Then now H
Okay.
alpha means, yeah, it's the red visible spectral lines of hydrogen atom. It is a red visible spectrum of hydrogen atom. Nothing. It's just that.
Okay.
Okay. Yeah.
Thank you,
Thank
ma'am.
you all. Thank you.